Hi, my name's Kevin Ellard, and this seminar describes the historical role of animals and zoonoses in emerging diseases for human populations, as well as their maintenance within these populations. This seminar forms assignment number 1 for VET640. Also, as part of the introduction, I currently work as a veterinary officer with the Tasmanian government and have been worked in government veterinary services for the whole of my veterinary career. First up, I thought it important that we should actually define what we mean by zoonosis or zoonotic disease. The World Health Organization website defines a zoonosis as any disease or infection that is naturally transmissible between vertebrate animals and humans. They go on to state that zoonoses may be bacterial, viral or parasitic, or may involve what they refer to as unconventional agents. I interpreted the term parasitic used in their definition to include organisms such as fungi, amoeba and helminth, and that unconventional agents refers to prions. Zoonoses, in addition, need not only be transferred through direct contact, but can also be transmitted via one or more intermediate species or via insect vectors. Zoonoses may also be transferred from humans back to animals, and this is commonly referred to as reverse zoonoses. In preparation for this assignment, I recently discussed the area of zoonotic diseases with my niece, who was about to graduate and begin working as a doctor. I was very surprised when she looked at me blankly when I mentioned the terms like One Health, and when she scoffed when I stated that the majority of human diseases had emerged from non-human animal populations. Clearly, the University of Western Australia's Medical School did not convey this area as a priority to my niece, so why should we be concerned about zoonoses here? After all, we live in a technical age where medical advances are occurring at an increasingly rapid rate. We have access to antibiotics, vaccines, nanotechnology, organ transplantation, and stem cell, in addition to everything else. In addition, human populations are increasingly living in urban environments away from wild animals and livestock, and thus why would their common diseases be of concern to us when really, what we hear about is diseases such as cancer, heart disease and diabetes from the media. To answer this question of importance, we must look at those diseases that have existed and are emerging in human populations. In a review paper of emerging diseases by Grieger, he stated that most human diseases are caused by pathogens that can actually infect multiple hosts. There are very few diseases that are restricted to human-only pathogens, and most of these have actually have ancestry with animal diseases. A review of 1,004 human pathogens known to exist found that 60% were actually classified as zoonotic. Within the large group of 1,400 pathogens listed, 177 of these were considered to be only recently emerged. Of this latter group, more than 70% were considered to be zoonotic. The standout group within this emerging group were the RNA viruses. If we want to look at the importance of zoonoses purely from a financial aspect, then the BSE outbreak in the UK has been calculated to have cost that country $6 billion. HIV and AIDS is currently calculated to be worth $500 billion, and the SARS outbreak $10 billion. More importantly, it's predicted that the cost of a future outbreak more importantly, it's predicted that the cost of a future influenza pandemic could be as high as $800 billion US. That doesn't take into account all of the social ramifications and the environmental costs that go with these sorts of diseases. Thus, two distinct trends have been observed during recent years. Firstly, diseases are emerging at a more rapid rate than has seen in the past, and a higher proportion of these emerging diseases are zoonotic. Within the emerging diseases, the RNA viruses are perceived to be the most important. This should be of no great surprise when we accept that the environment in which we live is also undergoing rapid change, and as this change occurs, so will the disease profile. This is not a new idea. The ancient Greek historian Plutarch noted this in his writings and stated that new classes of diseases often followed profound changes in the way humans lived. In addition, more recently, 200 years ago, Edward Jenner, the father of vaccines, stated that deviation of man from the state in which he was placed by nature seems to prove to him a prolific source of disease. Thus, in a joint WHO, or World Health Organization, Food and FAO and OIE working group, this group concluded that the drivers for this change were an increasing demand for animal protein, the associated expansion and intensification of agriculture production, the longer distances and more frequent distances that animals were transported, and live animal markets, bushmeat consumption, and the increasing trend of habitat destruction. It is at this point that I'd like to introduce the concept of the pathogen pyramid. The pyramid is designed to describe the emergence of new disease in human populations, but can also be used to describe the emergence of new diseases in other animal species, in particular livestock. I've used it with great success to describe the emergence of new diseases in salmon aquaculture in Tasmania, for example. As can be seen here, the diagram, which has been adapted from Woolhouse, has 4 basic levels. At the bottom of my diagram, there is a list of a series of boxes which basically represents a number of different species populations that could be contributing to exposure. Exposure 1, level 1, I beg your pardon, represents exposure. Level 2 of the pyramid represents infection, where the pathogen has been able to gain entry to the animal, and level 3 is transmission, where some transmission between the human host does occur. And finally, level 4 is the area designated for epidemic spread, or where major outbreaks of the diseases will occur. Each level represents an increasing degree of interaction between the pathogen and the new host species. The exposure level represents the continual exposure to potential microorganisms, and that is happening to us all the time, but very few of the microorganisms that we are exposed to are of any concern. Level 2 represents cases where these pathogens manage to infect the new host, as I said before. At this level, the majority of cases represent either dead hen hosts or disease that does not spread to other humans. However, a small number of these will continue up the pyramid to level 3. And it's at this level that infection can occur through contact with the reservoir population, as with level 2, or between individuals of the new host species. Finally, at level 4, as I said before, disease becomes established within the population and essentially can be transmitted easily between human to human, allowing disease to persist potentially without further contact with the reservoir species. I introduced the pathogenic pyramid now because I think it's an important concept, and I have used it to explain various case examples further on. So where I talked about level 1, 2 or 3 in the examples, this is the diagram that I'll be referring to. In a review of factors contributing to the emergence of disease that was written by Greger, it is suggested that the majority of modern human infectious diseases would have been absent from early man. In times when humans existed as nomadic groups, the small dispersed populations and the continual migration is thought to have protected them from a number of diseases. I'm a great fan of visual diagrams, and this one is designed to represent a small number of human populations in blue moving through the environment but not actually amalgamated into a single large population. You'll see a number of these diagrams throughout the rest of this representation, so I hope they make sense. Although early populations would have had regular contact with other animal species, this contact would have been largely through hunter-gathering activities. Their continual movement throughout the environment meant that they were always moving to new areas, and infection had little opportunity to cycle back to the individuals within the population. Should any infection establish, the limited contact between the populations or the groups meant that it was unlikely to spread throughout the entire population. These factors inhibited the establishment of pathogens, particularly those that had a very short environmental survival time, and also the development of human-specific infections. Most diseases present would therefore have been expected to be from animals in which the humans had regular contact with the reservoir hosts, or via vectors that were spreading them from the local species. Obvious exceptions would be diseases such as tuberculosis or anthrax, both which have long environmental survival times under suitable conditions. Tuberculosis would have also had the additional factor that having such a long incubation period, it would have been able to spread infection to other members of the population before causing death. A small number of diseases would therefore have been endemic at a low prevalence, and occasional disease events would have affected one or two populations, but the overall disease profile could have been expected to be relatively stable. This is not what we see today. So what are the factors that are contributing to changes in disease profile these days?